Welcome back to the second lecture of chapter 17. So at this point, you already understand what an acid and a base are based on the Arrhenius and Bronsted-Lowry definitions. So let's continue. Let's go deeper. And you also know about the acid and its conjugate base and the base and its conjugate acid. So new concepts. Distinguish between strong acids and weak acids. So a strong acid is going to be one that is going to produce or donate a lot of hydronium or protons. And the weak acid is going to be the one that only breaks partially. So how are we going to do this? Well, we're going to do it by understanding equilibrium constants. Because an equilibrium constant that is bigger than 1 favors the products, right? So if I have an equilibrium constant for the acid, that's what the 8 mean, equilibrium constant for the acid, then there's going to be a high concentration of protons or a high concentration of hydronium because the water is taking the proton. So we're going to be talking in terms of equilibrium constant. So a really big number for the equilibrium constant is probably an indication of a strong acid. A really small number like 10 to the minus 2, 10 to the minus 3, we're talking now weak acids. We can do the same thing for the base. So equilibrium constant for the acid, equilibrium constant for the base, and equilibrium constant for water. So those are the three equilibrium constants that are going to be super important that we understand in reference to acid, bases, and water. And we also not just going to do that based on the equilibrium constant, we're also going to do this based on the structure. For those of you planning to go to organic chemistry, these concepts are super essential to understand organic 1. We're going to be referring a lot during organic chemistry to the Ka, but we're going to be talking about pKa, which is nothing more than the minus log of the Ka. So for those of you looking forward to organic, I strongly recommend that you put a lot of effort to understand this very well. You either understand it now very well and breeze through organic chemistry, or try to learn it there where you're learning a lot of other stuff at the same time. So like I was saying before, we're also going to evaluate the strength of the acid on the structure based on electronegativity, the amount of oxygens, and so on. So you're going to have to refer back to Lewis structures in this case. So let's start with this. Classify each acid as a strong or weak acid. So this is the easiest part. We are not even using equilibrium constants on this one. What we're using is memorization or your notes because there's only 7 strong acids for general chemistry. Every other acid, and there's going to be thousands of them, are going to be weak. So here are the strong acids. Hydrochloric acid, hydroiodic acid, hydrobromic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. So there's 7 of them. So if it's not one of these 7, it's not a strong acid. As simple as that. It has to be one of these 7 acids to be a strong acid. We're going to see once we study the weak acid, we're going to see that some other strong acids are stronger than others. But to be a strong acid, it has to be one of these 7. These are the 7 that are generally accepted in general chemistry. Some books show 8, but these are the 7 that I'm holding you responsible for. The other one is not a general agreement as of today. So, first one, strong or weak? That's right there, so that's a strong acid. This is right there, so this is a strong acid. This is right there, so this is a strong acid. This almost look like this, but it's not the same. This is sulfuric acid. This is sulfurous acid. So this is weak. It's not one of the seven. As simple as that. If it's not one of the seven, it is not a strong acid. If the acid is weak, so that one there, right? So that would be the only weak acid we found. And acids, whenever we talk about acids, given that this planet and your body are almost 70% water, we're talking about solutions, aqueous solutions of water, of acid, so dissolved in water, mostly water. So if the acid is weak, write an expression for the acid ionization constant. So we know that the Ka is going to be the products over the reactants. And we know that it's going to be elevated to the power of their respective coefficients. So that means we need a balance equation. We cannot write the Ka unless we have a balance equation. And for the purpose of what we're going to be doing most of the time, we're always going to do this balance equation reacting the acid or the base with water. So the ionization equation for any acid or any base is going to be in the presence of water. So let's do that. So if I have sulfurous acid reacting with water, which is a liquid, this is a weak acid, so that means you're not going to have one arrow, you're going to have two arrows because it's going to establish an equilibrium because of its nature to being a weak acid. So you already saw how the acid reacts. So the acid is going to donate a proton to the water. So the acid is going to lose a proton. So from H2 it went to 1. This remains the same, but it lost a positive charge. So it should be negative because it was neutral. It lost a positive charge, so it should be negative to balance that. And it's going to be aqueous. And the water just gained a proton. So the water, which is neutral, just gained a positive charge, so it should be positive. So it's another polyatomic ion known as hydronium. And we talked about that on part A already. And this is going to be aqueous also. Is this balanced? Yes, it's balanced. So now we're ready to write the ionization equation, the ionization constant. So the ionization constant is going to be the products, hydronium concentration, to the first, multiplied by hydrogen sulfide, to the first, divided by the reactants, sulfurous acid, to the first, multiplied by water, to the first. We never put to the first, so let's take it out. And you learn in chapter 16 that the equilibrium constant do not include solid or liquid. So the water doesn't go there. If the water was being created, like there's no water and you're creating the water, then in that case, you have to put it there. And we're going to talk later why we do that. And that's how we do the ionization constant or the equilibrium constant. We call it ionization constant because it's producing what? It's producing ions, therefore ionization. But in reality, the proper name for this is the acid constant or equilibrium constant for the acid. So remember, if we are writing an equilibrium constant, it's because it's an equilibrium reaction. So therefore, you need two arrows. So therefore, you will never write an equilibrium constant for any of the strong acids because they do not create equilibriums. They go 100% to completion. So go ahead and do that. Classify each of the 4 acids as strong or weak. And if you happen to have a weak, write the Ka. Remember, you need a balance equation first. Do it reacting the acid with water. So what about this problem? Pick the stronger base from each pair. So bases take protons. So the one that takes the proton better is a stronger base, right? So how do we know which one is going to take the proton better? It's a super important concept for organic chemistry too also. Well, let's look at these factors. The stronger the acid, the weaker its conjugate base. So if we have a base, the stronger the conjugate acid, the weaker the base is. It's always the opposite, right? The stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. So let's start with that. Let's go ahead and write the conjugate acid. So the conjugate acid of this is going to be HClO. The conjugate acid of this is HClO2. The stronger the acid, so these are the acids, the weaker the base. We're looking for the stronger base. So this is one of the strong acids. This is perchloric acid. So this has to be the weaker base because the stronger the acid, the weaker its base. So this is one of the strong acids, so this has to be a very weak base. That means this is the stronger base because this is a weak acid. So we found our stronger base already. Okay? So what about the next one? The conjugate acid is going to be that, and the conjugate acid of this is going to be that. This is one of the strong acids. So this has to be the weakest base. This is just an acid, not a strong one. So this has to be then the stronger base. So far we have just used the first factor. The stronger the acid, the weaker its conjugate base, or the stronger the base, the weaker the conjugate acid is. So we are finding the stronger acid, which tells us which one is the weaker base, therefore the stronger base is over here. What about the next one? The conjugate acid is going to be that. The conjugate base is going to be that. Is any of these two one of the strong acids, one of the 7 we saw? No, they're not. Let me do it again. HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. So on this one here, none of those matches there. So we cannot use the first factor. So what is the second factor? If in the same period, the more electronegative element can better stabilize the negative charge on the conjugate base. The more stable the conjugate base is with that charge, the weaker it is. It's already stable. It's not going to mess it up taking a hydrogen. So this hydrogen is attached. So you need your Lewis structure, right? It's attached to a carbon, while this hydrogen is attached. Let's see, that would be attached. When you do the Lewis structure, you will actually have something like this. H, O, Cl. So the oxygen is the only one that can have the hydrogen and the chlorine attached to it. So ACN is the hydrogen is attached to the carbon. HOCl, the hydrogen is attached to the oxygen. Are carbon and oxygen on the same period? Yes, they are. They are both on period number 2. So the more electronegative element, the oxygen is the more electronegative element, can attract electronegative, right? That's the definition, can attract the negative charge closer to the nucleus. Secret of life, positive love negative. So because oxygen is more electronegative, it can attract that charge closer to the nucleus and be more stable. The one that is the more stable benefits the least from getting a hydrogen. And bases want to take hydrogen, right? So this base is a weak base because it's already stable. It doesn't want to take the hydrogen. So it doesn't want to do what bases do. So the strong base here is going to be that one. So this would be my stronger base. Clear this a little bit. So far we have our 3 stronger bases. So let's do this one once more. The Lewis structure is going to be something like this, which means the hydrogen is attached to carbon, and in this case, the hydrogen is attached to oxygen. Carbon and oxygen, they're both on the same period, and oxygen is the most electronegative one. So this negative charge on the anion can be better stabilized by the most electronegative one, which means it's already stable. There's no need for it to take a hydrogen or a proton to be more stable. So the one that benefits the most from taking the hydrogen is going to be the cyanide. And since this is the one that wants to take the hydrogen, this is the one that will win in a competition because oxygen doesn't need it, then this is the stronger base because that's what bases do. They want to take hydrogens or protons to be more specific, right? So that's the stronger one. So we know about how to find the stronger one by comparing the acid and then deducing the base. The stronger the acid, the weaker the base. We now know it based on which element stabilizes the electric charge better. So that would be the weakest base. And now let's do the last one. The last one, the conjugate acid is going to be HClO3. And the other one is going to be HClO2. Immediately you can say, this one is one of the strong ones. So this gonna be this is gonna be the weaker base, and this will be the stronger base. So that was simple. You basically recognized that the conjugate acid was a strong one, so the weakest base. Let's change the game a little bit. So let's say that we're not comparing those two. Let's say that we are doing that we are doing, let's make this one 2, which we already have, so we're going to change the other one also. So this one is 2, and this one over here is going to be just 1. So what about on this case? So let's do the conjugate acid first. This will be HClO2, and this one will be HCO. Chlorous acid and hypochlorous acid. Are any of them one of the 7 strong acids? No, they're not. So we cannot use this one to answer. The hydrogen is attached to a chlorine. The hydrogen is attached to a chlorine. So we cannot use that one either because they are attached to the same element. So what do we use then? The more oxygen atoms the molecule has, the better it can stabilize. There we go again, that word, stabilizing. Stabilizing. So the more you can stabilize this negative charge, the lesser the need to capture a proton, so it's not behaving like a base. So the weaker base. So which one have the most oxygens? These ones. And the reason for that is going to be resonance. So chlorine, when we do the Lewis structure, it's going to be like this. Hydrogen and chlorine that's combined. Then we put an oxygen over here with 6 electrons. Another oxygen over here with 6 more electrons. And then that leaves us with only 1 electron there, but because this is negative, we can put 1 more electron, therefore satisfying the octet rule. The other one will look like this. You're going to have chlorine again. Hydrogen brings an electron, chlorine brings another one. The oxygen brings 6 electrons. The another oxygen brings 6 more electrons. And another oxygen brings 6 more electrons, and we put the negative and we put it there. And that will be that one there. So this negative charge had to be distributed the best possible. So we got electronegativity pulling this way, electronegativity pulling this way, and electronegativity pulling that way. So this charge is being spread all over the, remember we're doing it without the hydrogen, right? So the hydrogen can go. So the negative charge is being pulled, is being stabilized by the electronegativity of those 3 oxygens. On this one, we have the same type of stabilization, but only toward 2 areas of the molecule. So this one definitely stabilizes the molecule better, therefore the weaker base. So this becomes, this one becomes the stronger base. So 3 ways to know. You can compare to the conjugate acid. So the one with the stronger conjugate acid will be the weakest one, so the other one will be the strongest one. You can compare to the electronegativity of the element if they happen to be on the same period, not different periods. You can look, if everything else is the same, then you can look at the number of oxygens. The more with 1 oxygens can stabilize the charge better, therefore the weaker base, because it's already stable, why mess up with that? And always the weakest base is the most stable base. Always the weakest base is the most stable base, which we saw with this and this. So with that in mind, and using those factors to consider, you're going to be practicing very soon. So before we go any further, construct acid and base ionization constant expressions. So if we're doing an acid, we will begin with an acid, let's say HF, which is a weak acid. We're doing equilibrium constant, so it gotta be an equilibrium. So that's there, so you say, oh, there's something wrong, there gotta be 2 arrows. This had to be aqueous, and this is an acid, so the acid is gonna lose a hydrogen. So it's gonna be negative, and the water will gain that hydrogen, becoming hydronium. And then we go back to chapter 16. So you're already experts on this part. So that goes there, that goes here. The water doesn't go because it's heterogeneous mixture, but this one goes there. And everything is 1, 1, and 1. So 1, 1, and 1, which we don't have to put in there, right? Neither here. We don't have to put ones on the balance equations, just for the purpose of illustration. What about, so this would be Ka because it's an acid. The reactant is an acid. What about Kb? Well, let's do Kb. Kb would be for a base, right? And it had to be a weak base. So let's begin with that base. Remember, water is amphoteric, right? So it can accept or donate protons. So in this case, it's going to donate a proton. So you're going to make HF, and the water is going to become hydroxide. So we're doing Kb. Kb is going to have the products over the reactants. Once more, is balanced. And last but not least, Kw. Kw is just water reacting with water. So water is amphoteric, right? So one of them can behave like an acid, the other molecule of water can behave like a base. So the one on the left loses the proton, so we end up with the conjugate base, and the water gains the proton, so we end up with the conjugate acid. So this was the ionization for water reacting by itself. So that's Kw. So Kw is nothing more than hydroxides times hydronium over what? Water and water over nothing. So that's what Kw is. So you basically have just that. So that would be Kw, which is super significant, because with this is how we're gonna define the rest of the chapter. Kw is the most important equilibrium constant in reference to acid and bases, because it gives us the base to understand, or the basics to understand everything we need to know about acidity and so on. So that's Kw, hydroxides times hydronium. So what did we learn on chapter 16? Any equilibrium constant will remain, indicates the tendency toward the products or the reactants, and the reaction that where that equilibrium constant came from is an equilibrium system. So anything you do to that equilibrium, Le Chatelier's will come into play, and if I increase the hydronium, right, then it's gonna turn toward the reactants, which means by doing that, the hydroxide is gonna come down. That way, the equilibrium constant will not be affected. So remember Le Chatelier's principle, right? That's what we studied that on chapter 16 and not now. If I, for example, increase the amount of hydroxide, it will turn toward the reactants to bring the hydroxide down, which will also bring down the hydronium in the process, because it's going toward the reactants, right? And that's so that the Kw doesn't change. The only thing that can change the Kw is a change in temperature. So as long as the temperature is the same, the Kw has to be the same. So important to know, the possibility of two molecules of water reacting with each other is 1 out of every 1, 2, 3, 4, 5, 6, 7. So 1 out of every 1 million. So 1 of every 1 million molecule will react with another molecule. In other words, the possibility is for one molecule is 110 to the minus 7. So one molecule, it have a possibility of 110 to the minus 7 of becoming hydroxide. Another molecule have also the possibility or the probability of 110 to the minus 7 of becoming hydronium. So our Kw value is going to be 110 to the minus 14. Base is the same, right? So we just add the powers. So Kw, the value for Kw at 25 degrees Celsius is 110 to the minus 14, basically room temperature. So whatever you do to the system, increasing the hydronium or increasing the hydroxide, is going to regulate itself by changing one or the other to remain at the equilibrium constant. And that defines everything we need to know about acids. So go ahead and work on that, what we just did on the prior learning check. And once you do that, let's do some more practice here. Based on the molecular structure. So, and we already started talking about that. Remember, I draw several Lewis structures, right? So based on the molecular structure, pick the stronger acid from each pair of oxyacids. So the stronger acid is going to be the one that will win on losing the hydrogen, right? So if this one loses the hydrogen, you end up with ClO negative. If this one loses the hydrogen, you end up with ClO negative. Which of these two conjugate bases is the most stable one? The most stable is going to be the one with the bigger, given that everything else is the same, right? Given that the negative charge is on the oxygen on both of them, then the bigger amount of oxygen makes the most stable one. The most stable base is the weakest base. And the weaker base gives us the stronger acid. So with that said, we just found the weaker base, so this had to be the stronger acid. The stronger acid would be the one that gives you the weaker base. And the weaker base is the most stable base. And in this case, having the bigger amount of oxygens stabilize that negative charge better. What about the next one? The next one we have CCl3OH. So we're going to have CCl3COOH behaving like an acid, producing CCl3COO negative, right? The other one is CH3COOH behaving like an acid, losing a proton, and it's going to give us CH3COO negative. And you may be asking, why did you took this hydrogen and not one of these? And the reason is this hydrogen is attached to oxygen with an electronegative value of 3.5. This one of these hydrogens is attached to carbon with an electronegative value of 2.5. Oxygen is the most electronegative, so oxygen can stabilize the resulting charge once the hydrogen is gone. So the acidic hydrogen always comes from the most electronegative element, because when the hydrogen leaves, the element that remains with the negative charge resulting can stabilize it more. So that's what that hydrogen goes instead of these hydrogens. So question now is, which of these bases is the most stable? If we find the most stable base, then we found our strong conjugate acid. So how do I know which one is the most stable one? The negative charge is on the oxygen. So electronegativity has nothing to do with it. What about the number of oxygens? There's two oxygens. So that doesn't help either. So do I have anything else in here? Number of oxygens, electronegativity, I cannot use any of those two. I'm trying to find the weakest base by finding the most stable, because the most stable will give me the stronger conjugate acid. So far I am nowhere. So now I'm gonna have to say, well, what's the difference? Well, let me do a Lewis structure to see if that helps. I'm gonna have carbon, double bond O, oxygen, attached to a carbon, and then there's a chlorine, and a chlorine coming out of that carbon. On the next one, and this is gonna be an ion, right? On the next one I have very similar, carbon double bond oxygen, oxygen with full octet, attached to a carbon that it have a hydrogen, and a hydrogen. So this is exactly the same, this part, so that cannot be a factor. So the difference is this carbon, because this carbon have chlorine, and chlorine, while this carbon have hydrogen, and hydrogen. And how does that help me? Well, let's go deeper again to Chem 1. Electronegativity of hydrogen is 2.1. Electronegativity of chlorine is 3.0, if I remember right. So that means there's going to be a pull going this way and a pull going that way, because 3.0 minus 2.5 is a polar bond. However, 2.5 minus 2.1 doesn't have polar bonds. So this is the most stable, because what happens? The negative charge, which is on the oxygen, is going to be pulled that way. So you see a pull that is spreading the negative charge on the oxygen all over the molecule. In here, it just remains there. It doesn't go anywhere. So this one can spread the negative charge across a bigger area, making it more stable, which means weaker base. Therefore, this is my stronger acid. The chlorine is far away from the negative charge is, but it causes that effect. We call that the inductive effect. So if you happen to have an atom on the molecule that can pull the negative charge across the molecule, that's what we call induction. And because the negative charge gets spread over a bigger area, then the molecule is more stable. An analogy I like to use to represent that, if I were going to explain that to a 6-year-old, I would say, where induction effect is like having a family, having a mom and dad with 5 kids on a 3-bedroom house. Mom and dad happens to be on the master room, and then the other 5 kids have to spread within the 2 remaining rooms. And there's going to be a lot of conflicts, because I used to live with three brothers on the same room. There's going to be a lot of conflict there. There's going to be a lot of stress. But what if they continue improving through life, going to school and doing all that kind of stuff, and then they can move, the 2 parents and the 5 kids, they can move to a 5-bedroom house. Now we're going to have mom and dad on the master room and 4 remaining rooms for 5 kids. At least everybody's going to be happy, but the last 2 remaining kids. And they're probably twins, so they don't mind. So the bigger the space to spread around, the more stable the family is going to be. The same with the molecules. The bigger the area to spread around that negative charge, the more stable that base is going to be, and the weaker. There's no need to take the hydrogen to become stable. So it doesn't want the hydrogen, so it's not behaving like a base. So the weakest the base is. And things that are going to allow to spread that charge, the electronegativity of the atom where the charge is, bringing it closer to the nucleus, or elements down the molecule that can attract that charge also and spread it over the 5 bedrooms on the bigger house. So the more stable you can visualize the molecule, the weaker the base is going to be, the stronger the conjugate acid is going to be. So with that in mind, go ahead and do that problem. Explain your reasoning. Always think about the analogy with the 6-year-old that you have to explain this to, and then bring it up to the college level. So we already know what Kw is. I told you Kw is, once we consider that only one out of every million molecules can carry out a reaction with another water molecule, that's what Kw is. 1 times 10 to the minus 14. And remember, equilibrium constant do not have units. And this is what I just showed you. So I got ahead of myself, but now you can see it better. And there's no unit there. I don't know what that's doing there, and it's been there for the last several semesters. So equilibrium constants have no units. And with that said, now you understand how to take an acid and do a balance equation with water, showing the ionization process, and then you can do the Ka. You can do that the same thing with a base because water is amphoteric and it can take or give, right? And now you saw where the Kw is coming from. And we saw how we can evaluate the strength of the acid by memorizing the 7 acids and just saying because of this, or by looking at the molecule even down to the Lewis structure level, thinking about electronegativity and now thinking about the inductive effect. You basically have the first week of organic chemistry. That's what we do on the first week of organic chemistry. We review all these concepts that are going to keep repeating during the organic chemistry class. And with that in mind, next time we meet, we're going to be on part C of the chapter, where we're going to start doing calculations using Kw and every single formula that we can derive from Kw. So until the next time, see you later. Take care.